So last time we introduced the formulation of the RG transformation, and today we will continue formulating this RG transformation in 1 and 2 relevant variables. And we have shown previously that for 1 relevant variables, we are able to get the scaling relations by this repeatedly iterating these RG transformations infinite number of times. And this correlation length diverges, and we can extract this eigenvalues of this transformation matrix M, and as a power law dependence on the scale factor B. And today we will continue looking at this RG transformation for 2 relevant variables, in particular for the matrix M being diagonal. So let's just start by writing down this free energy density as a function of this scale factor B before and after this coarse graining procedure, and there's a b to the power minus d factor in front of this transformed free energy as a function of T prime and H prime, where T prime and H prime are the transformed temperature or reduced temperature and reduced magnetic field, and the prime and unprimed variables differ by this transformation matrix element RBT and RHB, which describes how this temperature and field are transformed under these RG transformations. Of course, most cases, if T represents temperature and H the fields, then T and H are orthogonal directions, so they don't mix. And as a result, this RBT and RBH are just functions of T and H only. But in general, we can consider the 2 variables are just transformed under this most general linear functions, linear transformations. And as I described last time, that in this RG transformation, we will end up to be close to the fixed point value of these parameters or variables, which we call this T star and H star. And at this fixed point, if we keep transforming these variables at the fixed point, and these variables won't change their values if they are sitting exactly at the fixed point. But these critical properties can be analyzed by analyzing this RG transformations close to the fixed point, only close to the fixed point. So if you are very far away from the fixed point, then this analysis doesn't work. So we need to be very close to this fixed point in order to see the divergent or singular properties of various observables. So then we could linearize these transformations when we are very close to this fixed point values, and we can define this delta T and delta H, which are the deviations of temperature and the fields from their fixed point values. And then we could linearize the RG transformations in such a way that we can perform the further RG transformations when we are very close to, but not exactly at the fixed point value. And so then we could denote this transformed delta T and delta H as delta T prime and delta H prime. So in general, this delta T prime and delta H prime are a linear function of delta T and delta H, and they are related by this 2x2 matrix, where the matrix elements are nothing but this derivative of this transformation matrix element RBT and RBH respect to this temperature of the field. So the first column is the temperature derivative of this RB matrix element, and the second column is the field derivative of this RBT and RBH. So in general, they are not zero. Okay, so you got 2x2 matrix, and we could find the eigenvalues by diagonalizing this 2x2 matrix, and that's easy. But in most cases, T represents temperature and H the field, and they don't mix. Okay, because temperature and the field are not to be dependent on each other, because they are regarded as the independent parameters or variables. In other cases, they may mix up. But let's just start from the very simpler case where they don't mix up. When that happens, you don't have this off-diagonal matrix element, and all these off-diagonal matrix elements are 0, and the diagonal elements are your eigenvalues, okay, which we denoted them by this lambda bt and lambda bh, where this lambda bt is actually b to the power of yt, and lambda bh is b to the power of yh. So that's from the previous definition. So now we could just plug in these RG transformations, and we get to this diagonal 2x2 matrix acting on this t and h, and you get this t prime h prime. So then we could imagine we iterate this RG transformation n times, and our correlation length would pick up the factor of b to the power of n in front, and this correlation function now becomes b to the power of nyt times t and b to the power of nyh times h as independent parameters. And this is the correlation length as a function of the scale factor b, and we know that when h is equal to 0, then correlation length diverges as t to the power of minus nu, and when that happens, you simply just set h equals 0 here, and then this, so you can simply just compare this two sides of this formula here, and you get nu is actually 1 over yt as we mentioned last time. And you can also set little t to be exactly 0. We're sitting exactly at transition temperature, and in that case, this C0h now become b to the power of n times C0 and b to the power of n yh times h. When h goes 0, limit, this is simply just h to the power of 1 over yh with a minus sign here. So from these expressions, we are able to derive the scaling relations that we mentioned previously. We take a short break, and we'll come back. We will, starting from these two expressions, and we can derive this previously mentioned scaling relations of these two. Okay, so let's take a short break. So let's continue deriving these scaling relations from RG. So before the break, we just showed that this correlation length after n iterations under RG expressed in terms of this b to the power of n times c, that's function of this rescaled t and h. And now, but we could use this information and plug into the free energy after this n times RG transformations. And under n time RG transformations, this free energy density carries b to the power of n minus nd factor, and the multiplied by the free energy density in this rescaled variables. But the rescaled variables are nothing but these factors that we just defined, and so we could plug in these definitions of the rescale factor t after n RG iterations, and also this rescale factor of h after n times RG transformations. And we could set this factor b to the power of n any scale we want, and we could choose this scale to be some constant b bar times t to the power of minus 1 over yt. And if we choose so, and we could simplify this free energy density as function of the scale factor, and now this rescaled free energy density becomes a simple form as a function of a b bar and h over t to the power of yh divided by yt. And you can compare to the scaling hypothesis that we introduced earlier, say for example this Wheaton's scaling form, and you immediately get the scaling relations. So this should be 2 minus alpha, that in the exponent of this free energy density as function of little t, some power, and then delta is nothing but this ratio. Okay, so we have derived such relations many times. Now we could see very clearly the advantage of using the RG transformations to derive the scaling relations and also critical exponents. Because number one, the scaling relations and the scaling hypothesis could be derived from this kind of RG transformation after n times. And number two, those critical exponents like alpha, nu, and so on, delta, are nothing but these functions of yt and yh. But yt and yh could be derived, calculated from the eigenvalues of this RG transformation matrix M that we just introduced. So everything we need to know could be derived from the RG transformations. So the scaling form and also the critical exponents, and so that's what we will do. Okay, next we will use a concrete example such as one-dimensional and two-dimensional Ising model as an example to illustrate how this works in RG transformation. But before we do that, so let's just discuss one important remaining subject, which is called irrelevant variables. Remember that both t and h are relevant variables on the RG that we showed earlier, but in many cases, the Hamiltonian versus some model systems not only depend on these relevant variables, but also depend on some irrelevant operators or irrelevant variables. And we know very well on the RG transformations, the eigenvalues of the irrelevant variables are smaller than 1, so that they keep decreasing, shrinking the size of the eigenvalues and importance of that couplings until after an infinite number of iterations, they are gone. So we can disregard those irrelevant variables. So that's the ideal case, and we keep only the relevant terms in the Hamiltonian, and we could just disregard this irrelevant term. But there's a tricky thing. Some irrelevant variables are dangerous irrelevant variables, as I will explain to you in just a moment. So you could just perform such RG transformations on the free energy density, as I mentioned over there, including the RG transformations for the relevant terms and also the irrelevant couplings. So in particular for irrelevant terms, you get this factor, scale factor L to the power of y3 and L to the power of y4 for this K3 and K4 variables, which are both irrelevant. And remember that this y3 and y4 exponents are negative, so that when the scale factor B or L grows, and this prefactor in front of this K3 and K4 is actually become less than 1, so that it shrinks and shrinks and shrinks, and eventually after n iterations, you can see that L is our B factor, which is larger than 1, and y3 and y4 are exponents negative. So clearly you will find the scaling form of the free energy density looks precisely over there, except now you get the extra degrees of freedom which are related to the irrelevant variables. So ideally, when temperature approaches critical temperature, little t approaches 0, this K3 and K4 will shrink to 0 because of this power law dependence, since y3 and y4 are both negative. So this prefactor in front of K3 becomes t to the power of minus y3 over yt, which is t to the power of absolute value of y3 over yt as exponent. As a result, as t goes to 0, this positive exponent of t power law also vanishes. As a result, you can naively just disregard this irrelevant term. However, there's a very big but. So we could disregard this yk3 variables only when this free energy density is function of K3. When K3 goes 0, is analytic. Suppose that this f function, this free energy density, as a function of K3, becomes singular or non-analytic when little t goes 0 limit. So it does not approach just to a constant or a 0 or some non-singular value. But if this is a singular value, when K3 goes 0, you could not just ignore this if that happened. And when that happens, when this free energy density as function of K3 becomes singular, when that happens, we call this K3 a dangerous irrelevant variables. So in other words, we cannot simply just disregard this dangerous irrelevant variables simply because they carry its negative exponents after RG transformations, but we should keep this dangerous irrelevant variables in our scaling form, because this dangerous irrelevant variables will lead to some non-trivial extra anomalous exponents that will modify our scaling relations and also critical exponents. And we probably don't have time to discuss how dangerous this irrelevant variables is. You could check our reference and textbook on this phi-4 theory of the Landau free energy density. So this quartic term, this u term, which is proportional to this phi-4, becomes the dangerous relevant term. So you cannot disregard this U from this 5-4 theory when the dimension is actually close to 4 or upper critical dimension. So this is just to remind you that some irrelevant terms have this issue of the dangerous irrelevant variables. So we cannot simply just disregard all this irrelevant term, even though it seems that we are okay to do so, but we need to check whether the free energy density as a function of the irrelevant variables shows a regular or singular behaviors as little t approaches 0. So that's most of these formulations regarding this RG transformation, the scaling hypothesis and critical exponents and so on. So next we will illustrate these formulations by providing you with a concrete example starting from the one-dimensional Ising model to the two-dimensional Ising model on triangle lattice, and so that you will get more concrete ideas how this RG works. And then we end our semester's course perhaps this Thursday. Okay, so unfortunately there are some remaining topics I plan to tell you cannot be covered during this semester. Okay, so let's take a short break. So we're about to illustrate this RG procedure from a very simple one-dimensional Ising model, but before we go on, let me just define this RG transformation in a differential form, which is very useful when we perform this RG analysis to almost all these model calculations. So in other words, we do not just consider RG transformation as a very large change, but we consider a very small change in the scale transformations. Namely, imagine that this lattice is expanded just a little bit bigger. In other words, this scale factor b within this differential form of RG transformation is slightly larger than 1. So let's just slightly expand this lattice from this a to actually 1.01 times lattice spacing. So let's just expand this lattice constant to actually 1% or 2% or a few percent. And then we could monitor how this coupling constant flow under such infinitesimal RG transformation. So that's is particularly useful when we try to derive this RG scaling equation or recursion relations. And this differential form of RG equations is in terms of the differential equations. And we solve the differential equations as a function of the coupling constant as a function of this scale factor. And then we could find out how this coupling constant flow. So imagine this is my lattice, and with the lattice constant A, and we perform this block spin transformations on this lattice. Once we perform this coarse graining procedure, and the lattice spacing becomes larger, and the new lattice spacing is L times A, where L is larger than 1. Imagine that I could keep expanding this coarse-grained Hamiltonian even larger unit cell and larger by the factor of S times LA. And S now is a parameter which runs from, say, 1 to infinity. So then I'm asking this question, so how does this coupling constant flow under such scale transformations? And the particularly useful form of RG equations, when we set this S is actually 1 plus epsilon, where epsilon is actually infinitesimal amount of shift. So this epsilon is almost 0, but now let's imagine that this scale factor S is just slightly larger than 1. And then we could formulate this differential RG transformations by taking the derivative of this coupling constant with respect to this L and taking a limit when epsilon goes 0, and this limit is defined as the difference between the coupling constant at SL and at L, and divided by the change of your lattice constant from, say, SLA to LA, so that's will be, the difference will be epsilon times L. So little a is regarded as just unit 1, so I simply just forget about this a. So then you could define that kind of differentiation as a function which is related to the derivative of this transformation matrix element are S with respect to this S when S is evaluated at L, or S is evaluated at simply just 1. And we could denote this differentiation as some function unknown, which we will derive, which we call this B, capital B, as function of the coupling constant at the original length scale LA divided by L, or LA. So now this differentiation or differential equation of a coupling constant could be formally defined in the logarithmic scale, where tau is defined by this log L. Okay, so you could just take the logarithmic derivative of this coupling constant with respect to this log L, which I defined as d by d tau. And on the right-hand side of the differential equation, which is the matrix element of this transformation matrix M as a function of this coupling constant at that scale. So this is a standard form of the RG scaling equations in terms of the logarithmic scale of your length scale. And the fixed point value is reached when this function B on the right-hand side of the equation vanishes, which means that this coupling constant, when taking this with respect to this tau, vanishes, which means that this coupling constant is a constant of L, or log L, when right-hand side of the equation vanishes. And that is the definition of the fixed point, because the fixed point is the point where the coupling constant doesn't change under RG transformation. That is exactly what happens here when the right-hand side of the equation vanishes. So then this differential equation for coupling constant flow is very, very useful because it allows us to find out where this fixed point is. You simply just try to derive this RG differential equation of this form, and once you find out what the right-hand side function is, and you simply just look for the roots where the right-hand side of the equation vanishes, and the roots tells you where this coupling constant is when it is at fixed point value. By analyzing this fixed point value and this linearized equation based on this differential form, you are able to extract all this information that you want. And this is particularly useful when we derive the differential form of the RG transformation in momentum space, so-called momentum shell RG, but in real space we can also do that. So let's look at this particular example of one-dimensional Ising model from RG point of view. So remember, we have discussed that early on when we talk about this one-dimensional Ising model, which can be solved exactly and very easily. But now let's try to get to the same solutions from RG point of view. So this is the Hamiltonian of the nearest neighbor coupled Ising ferromagnet, where K is simply just a reduced dimensionless coupling of Ising term, and all those spins are living in the one-dimensional chain. So what is the coarse-graining procedure for this? Consider that you could sum over the partial spins. For example, every other spin, every second spin is a circle surrounding that dot. You actually perform this partial trace over all such spins that are encircled by this little red circle. So the way that we perform the partial trace is by writing down the partition function of this one-dimensional nearest neighbor Ising model, and we could decompose the trace or summation over all the spin on every side into two parts. One is the remaining part, and the other is the part that involves only the red dots. So we could sum over the spins on the red dots, and each red dot connects to two neighbors, right? So you need to encircle three sides. The middle side is the spin that we want to sum over, but there are S1 and S2 that connect to the sigma in that term right there. So we need to sum over the sigma. And when we do so, you get a very simple form, which is 2 times coach of K times S1 plus S2. And we know that this has to be equal to the coarse-grained Hamiltonian, which is the Ising coupling between the blocks, and which we call this k prime S1, S2, because the Bloch spin is also in terms of the S1 and S2, but the Hamiltonian can be expressed in terms of the same Ising form only with the modification of the coupling constant. And the coupling constant now becomes k prime, and so we need to find out the relation between k and k prime. So that leads to two possibilities. One is when S1 plus S2 becomes 0, and another is when S1 and S2, S1 plus S2 becomes plus minus 2. So either they get cancelled or they are added up. So when they are cancelled, the relation tells you that this equal to 2 equals a times e to the minus k prime. But when they are added up, and this is 2 coach 2k equals a times e to the k prime. So it's simply just plugging these two different cases. Either this is 0 or plus minus 2. Okay, so you could just combine these two conditions and you get to this relation that this is the so-called RG recursive relation between this unrescaled coupling constant and rescaled coupling constant. So k prime is a function of k through this equation here. Of course, this relation is not written in terms of this differential form over there, but this is in terms of the real space coarse graining RG procedure, and oftentimes for such a simple model, we could simply just get the exact relation between k prime and k. And we could use the equivalent relation, which tells us that hyperbolic tangent of k prime is actually hyperbolic tangent square of k. But we perform such a partial trace over every second spin. And we know that for finite k, hyperbolic tangent of k is always less than 1. Therefore, you could imagine that I could keep performing this partial trace second time, 3 times, infinite number of times. So after infinite number of times, hyperbolic tangent of kn goes to, say, hyperbolic tangent 2n times 2nk. So this goes like hyperbolic tangent square to the power of n. Of course, this approaches 0 when this number of iterations becomes infinity, unless this k goes to infinity. And that is precisely where the fixed point value is. So the fixed point values are either k star being 0 or infinity. And we know that this k refers to Ising coupling J divided by kBT. So when k star is 0, and which means that its temperature becomes infinity, right? And this is stable paramagnetic fixed point, which is trivial. And the non-trivial fixed point occurs when k star is infinity, and where this temperature is 0. And that is the Ising transition at 0 temperature for a one-dimensional Ising model as a critical point, or this critical temperature. So I guess that's the simple calculation based on the RG transformations and the coarse graining Hamiltonian and the relation between this k prime and k, and we could iteratively apply in such a RG transformation, and we get this fixed point value, which is nothing but what we discussed earlier. Okay, so we can base on the solutions and we can calculate this correlation length and divergence and this critical exponent and so on. But let's take a short break. So let's quickly go through the calculations of a one-dimensional Ising model. And once we know the fixed point value is that k star being infinity or 0 temperature limit, and we are able to calculate this correlation length near this fixed point. So remember, the relation between k prime and k is that hyperbolic tangent of k prime, this hyperbolic tangent square of k, and when k goes to infinity, in that limit, we can Taylor expand this hyperbolic tangent function, because remember, this hyperbolic tangent function is almost when x goes to infinity. So near that limit, we could Taylor expand this hyperbolic tangent function, and we get this approximate form which relates this k prime and k near that fixed point. So after the n iterations, we get factor of 1/2 to the power of n in front of this e to the 2k, which is equal to the e to the 2 times kn, okay, near that fixed point. So, and we know very well that correlation length in the one-dimensional Ising model goes exponential form of j over t, or e to the k So, and we could choose this n such that this e to the 2 times kn is actually almost 1, and we could just play the same trick that we did earlier, that by relating this correlation length before and after n RG steps, and we could get to that relation. And we could set this CB as the pre-scaled correlation length, which is order of 1, but after n or infinite number of iterations, you get b to the power of n as a prefactor in front of this order 1 value for correlation length, and therefore the correlation length diverges as 2 to the power of n, since this scale factor b now becomes actually 2. So this is nothing but 2 over there. Okay, so now you could actually compare this form with the standard form correlation length for one-dimensional Ising model, which is exponential of k. When k is close to k star, this is e to the k star, where k star goes to infinity, and that is actually 2.7, some power, which is infinity, and which is more or less this factor, 2 to the power of n, where n goes to infinity. So now you can see that this correlation length calculation for the correlation length more or less reproduces what we have earlier for this exact solution of one-dimensional Ising model, and it shows a very efficient way of analyzing this fixed point and this critical exponent and so on. So this is for the ferromagnetic one-dimensional Ising model. What about this one-dimensional anti-ferromagnetic Ising model, where you have alternating spin configurations along the chain? So if we just follow the same procedure that we did for the ferro by averaging over every second spins, then we end up with some trouble, because once we average over every second spin, which by chance are pointing down, and then we remove all these downspin configurations, and the system becomes a ferro, which is not allowed because we cannot change the symmetry of the Hamiltonian. So therefore, the anti-ferromagnetic Hamiltonian cannot be reduced to the ferromagnetic coupling. So what can we do? Well, the easiest way out of this trouble is by grouping up and down spin as a unit, and you sum over every second group of this up-down spins. In other words, you don't look at just a single spin, but 2 spins and 2 neighbor spins, which already are paired up, and therefore when you remove this orange bubbles, and the remaining system is still an antiferromagnet, right? So because the spins, all of this bubble is actually down, up, down, up. So we can actually use the same trick, but by organizing the spins in a different way, so that the antiferromagnetic nature of the problem is still preserved, and everything else is the same. So next, we should study this 2-dimensional Ising model on triangle lattice, which has been done by Onsager long time ago, and he was able to get the exact result of this triangle lattice 2-dimensional Ising model. But we will apply the RG procedures on this model again. But before we do that, let us just outline the Onsager results. So the main results of the Onsager solutions are the following. There's alpha exponents, which describe this singular behavior in the specific heat coefficient, and also alpha is actually 0, and it's delta, which describes this magnetization as functions of field, it's actually 15. Okay, so this comes from Onsager's exact results, and we can take these results and fix all the other exponents by the scaling relations that we derived previously. So, for example, if we look at this relation, 2 minus alpha is nu times d, and when alpha is 0 and d is actually 2, so that leads to nu being 1. And the yt exponent is actually 1. Remember that. Lambda t is actually L to the power of yt, and that is square root 3 for this triangle lattice structure. And we can also look at the other relation that we derived earlier, which relate this dimensionality YH and eta, the anomalous exponent eta, and you could use the related relation where you take the ratio between d plus 2 minus eta and d minus 2 plus eta, and that ratio becomes delta, and delta is 15, so d is actually 2, so you obtain this anomalous exponent eta being a quarter for triangle lattice Ising model. And from that you could derive this YH is actually 15 divided by 8, and lambda h is actually 2.8. So that's the reference point that we will stand, and next time we will start to use RG for this two-dimensional triangle lattice Ising model, and then we approximately get to this Onsager's exact results. Not, of course, the RG is not the exact method, but approximately this method will lead to the same results as the exact result. Let's stop here for today, and see you on Thursday.